In this example 3, in the Laplace transform, we are now going to do something a little bit different. We will be asked to compute y of t. We are given the input x of t, and we're also given the initial conditions. And we will now practice the zero state as well as the zero input response computation. Remember that the zero state is example 2. We have computed example 2 using just the input with the initial condition relaxed. Relaxed here means no initial condition. A system is relaxed means the system has no initial condition. In the next example, example 2a, which is on the next slide, you will see that I'm going to compute the same question. This is the same question. The impulse response is the same, but with the new given initial condition. We call this the zero input response. The response only due to the initial condition. The system is not relaxed. And the input is 0. That's why it's Zi, 0 input. So here, alright, we have zero state from example 2. We have Zs, zero state due to example 2. We have Zi due to example 2a. And together is yt. Now, we already know that if we have already computed Zs, we do not need to compute again. So we are only going to compute Zi this time. Okay, so now we have cosine 1t. I've again forgot to put ut. We're only interested in the causal cosine. We send our system into ht, which is the same ht as example 2. And now the initial condition is y0 at time 0, y is equals to 3. The output is already 3 at time 0. That's the initial condition. Okay, so let's again practice this. Xt equals to cosine 1t. Its Laplace transform is s over s squared plus 1 squared. 1 squared is 1, so it's 1. Laplace transform of ht is 1 over s plus 1, so that's trivial. And we have y of s equals to h of s multiplied by x of s. So you might be stuck here. We are now in y of s. We are given y of 0 in time. And now we are already in the frequency s domain. How do we introduce y0 into the s domain? We can't. So what do we do? Well, we know this relationship. Y of s equals to h of s, x of s. So we are going to replace h of s by 1 over s plus 1. So the unknowns is y of s and x of s. We can then open it up. So s plus 1 times y of s is equals to x of s. So here is the trick. We again open it up to be s ys plus ys equals to xs. Now here is the trick. We perform inverse Laplace transform to get the differential equation. And what we do now is we again take the Laplace transform of this differential equation so that we can now finally introduce our initial condition here. Okay, so this is the one big round, yeah? It went from time to the Laplace domain, the Laplace domain to the differential equation describing the system, and then back again into the S domain to introduce the initial condition. So this is where we put y of 0 in. Okay, so once we have this, now what happens? Then we can do, of course, the normal things to do the algebra to get y of s on one side, and of course x of s the other side. Now what happened is this. This is the initial condition. In example 2, the initial condition was 0. But now y of 0 minus y of 0 needs to move to the right hand side. S plus 1 is moved to the denominator. So this guy, this thing, is due to the input condition. Sorry, this guy, x of s divided by s plus 1, is due to the input. It is called the zero state response. What about this one? This guy? This guy? The response is y naught over s plus 1. The response due to the initial condition y naught. We already have solved the zero state response. The zero state response was found in example 2 here. So I'm not going to do this again. Once we have the S domain of ys zero state, we can find yt of zero state, which is these two terms here. Now all we need to do is to figure out how to solve the new expression due to the zero input. Y naught over s plus 1. What is y naught? Y naught is 3e over s plus 1 is simply the inverse Laplace transform is 3e minus 1t. This term is the output due to the zero input, or should I say it's to the initial condition. This is yt due to the zero input. It is 3e minus 1t. Remember, we are interested in the complete response, which is y0 state plus y0 input. So let's go and find the zero input. This is the zero input, and the other guy is the zero state. Alright, now look at this very carefully. These two terms is the transient. The transient response, because after time goes to infinity, these two terms goes to 0. The transient response came from two places. One from the zero state, one from the zero input. While the steady state simply came from the zero state, from the input. So this is a very nice example. Please learn how to do this example well, and you have lots of practice later on in the lab and the tutorial as well. We will now use MATLAB to see the response. The blue is due to the input. So again, the input is 1 cosine 1t. The final output is here, the red cross here, is 0.7071 cosine 1t minus 45 degrees. You go on forever as long as the blue line comes. What about the two transient response? Well, this guy, the green guy here, is due to zero input. The equation is 3e minus 1t. So see, it began at 3 at time 0, and it comes down very quickly, and about after 4 seconds later, it is almost stable, and wow, it is almost 0. So it doesn't contribute to the output anymore. What about the green guy here? This green thing here? This guy is due to the zero state. It is due only to the input. It has a transient, and then it becomes stable. So if you forget this curve, go to example 2 and take a look. Together, the two green guys add up to the crosses, the cross line, which is the complete response. Right, how do I solve this? Let's see this. Again, I use the symbolic for the MATLAB, and I set omega equals to 1 for cosine 1t, and theta equals to 0 means plus 0, so we can ignore plus 0. And we first take the Laplace transform of e minus 1t for the impulse response to get h of s. We'll define what is x of t in time, and we'll take the Laplace transform of xt to get x of s, and therefore now we get h of s times x of s. Now we have a term plus y naught. Where did plus y naught come from? It came from here, this equation. Let's see. Y of s is equals to h of s times x of s plus y naught. And in this example, h of s for the 0 state and the 0 input is the same. You should think why this is so, but from this equation, the h of s is simply 1 over s plus 1. Right, and then of course finally, once we have ys, we can find yt, and then the rest is nothing but plotting, as well as showing you the 0 state and the 0 input response independently. With that, we are finished with 0 state and 0 input. Thank you.